So we're always going to have an objective function that we're going to try to max or min. And then we're going to say subject to, and we don't write that out. We just write out ST constraint. Now you can have more than one constraint. Normally, when we have lots of constraints in this methodology that we're doing here, normally when we do this, those constraints control the problem, and wherever the constraints cross, that's kind of where we're going to end up. Okay? And that's really not a lot of fun. So we're not going to do multiple constraints in chapter 12 because there's really not much value in that. We're going to talk about multiple constraints in chapter 13 when we have a way around the constraints controlling us. Okay? So some terminology related to that is the word binding. If we're getting less than we could because we're on the constraint and the constraint won't let us get to where we want to be, then we say the constraint is binding. If the constraint is controlling our problem, if the constraint is keeping us from really finding the maximum or the minimum, okay? And you are bound by your constraints all the time, right? You think, hey, I would like to go to Tahiti on vacation, but you end up going to Henderson on vacation because that's all you can afford. Your constraint is binding, okay? You want to go out and have a nice dinner, but you're at Taco Bell because the stuff in your wallet is binding on you. All right? So most of the time in these problems we're about to do, the constraint is binding. And when it's not, it's somehow because this is the best we can do and we just happen to be on the constraint and at the best point all at the same time. Here in indifference curves, we always have a whole bunch of indifference curves, and we always told you in 302 that you want to be there. Well, that constraint is binding. We'd rather be here, we'd rather be at B than A, but we can't get to B because our constraint, that line, right? That line, yeah, that's a beautiful line. That line is binding on us and keeping us from getting to where we'd like to be. Okay? So constraints are binding. Now, we're going to set up something called a Lagrangian. A Lagrangian. And in the Lagrangian, we're going to deal with this constraint. So again, we're going to say, let's say that I have a utility function where my utility is a function of x and y, two goods I can buy, x and y. But it's subject to the constraint that I have a budget and the price of x times the amount of x times the price of y times the amount of y. So my budget is going to constrain me, and this is how much I'm spending on x, and that's how much I'm spending on y, and together those two things are going to be equal to my budget. Okay? So I'm going to write this out, and I'm going to write it out something like I want to max u, which is a function of x and y, plus a new variable called lambda, b minus px x minus py y. Okay? And I'm going to write out an equation that looks like that. And then I'm going to find the partials of this. I'm going to find f of x. I'm going to find f of y. And I'm going to find f of lambda. And then when I build my Hessian, and I know this excites you to no end, I'm going to have to include lambda in the Hessian. Oh, yeah. Oh, baby, baby. Okay? Baby, baby. Ooh, baby, baby. Okay? All right. So let's try one. Let's say I have this equation, z equals 150 minus 3x squared minus y squared. All right, I'm not going to put a constraint on it. I'm just going to solve it the way it is. Okay? And so I would find the partial of z with respect to x, which is fx, which is minus 6x. I'm going to set that equal to 0. That means x equals 0. Okay? I'm going to find dz dy, which is f of y, which is minus 12y. Set that equal to 0. Again, y equals 0. So the best I can be is where x and y equals 0. Yes? 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 Okay? And the value of z is 150. Okay? Now what do I do? Well, now I need to find my Hessian, and that's going to be minus 600 minus 12, right? Which is fxx, fxy, fyx, and fyy. I'm going to find those. I'm going to solve that, right? So that's minus 6. So h1 is minus 6. Okay? And h2 is minus 6 times minus 12 minus 0 times 0 is 72. So h2 is positive. I look at those two together, and what have I done? This is a maximum. Okay, you're like, well, that was simple. Yeah. Now, let's add a constraint. Let's say I want to max z equals 150 minus 3x squared minus 6y squared, subject to 10 equals x plus y. Okay? Good? Now, if I said subject to 0 equals x plus y, you'd still have an infinite, the constraint would have an infinite number of outcomes still, right? Because 1 and minus 1 still works. If we limit ourselves just to positive numbers, then you only have 0. But the optimal would be if this were 0, if we set that equal to 0, the optimal point would still be 0, 0, and the constraint wouldn't be binding on us. We'd get exactly the same result we had before. Okay? But we're not going to get exactly the same result. So we're going to say z equals 150 minus 3x squared minus 6y squared plus lambda times 10 minus x minus y. Okay? Do you see how we turn this into this? 10 minus x minus y should equal 0, right? If the constraint's binding? Yeah. And then we have our little friend lambda. Our friend lambda. So now we're going to take the partials of this, right? And we're going to get, zx equals minus 6 minus lambda equals 0. So you can say f of x, or you can say z of x. Yes, minus 6x, right? And you can say f of y is zy is minus 12y minus lambda equals 0. And you can say f of lambda, which is the lambda, is the constraint, 10 minus x minus y equals 0. Okay? Is that exciting? Yeah, it is. So these two things now have to be equal. So the answer is, right? So I say minus 6x minus lambda equals minus 12y minus lambda, right? And get rid of the lambdas. That's 6x equals 12y, x equals 2y. Now I can put that into here, and what answer am I going to get out? Well, I'm going to get out that x is 6.67 and y equals 3.33. Those are going to add up to 10. And that's going to be the optimal point. Is that exciting? Yeah. Okay, now I did that as an example, but it's kind of let's try it differently, just where we change the constraint. Okay, what happens if we change the constraint? So subject to 12 equals x plus y. Okay? What's going to happen now? Well, that optimal point is going to change. So zx equals minus 6x, and, right? No, minus lambda equals 0. So I didn't write this out for you because, in my brain you already know what you're doing. But we'd have an equation that says z equals 150 minus 3x squared minus 6y plus lambda times 12 minus x minus y. Okay, that's our Lagrangian. So people will say, oh, I have a Lagrangian. Well, that's what they mean. That's their Lagrangian. Lagrangian. Okay? Okie dokie dokie. Dokie. No? Don't we like that? Okay. So what's lambda? He said, while we're here. Well, lambda equals 12 times y. Yes? So lambda equals 40. Now, what's that 40 mean to us? Let's just keep that 40 in the back of our minds, right? What's z equal to now? Z, this. Well, z is 150 minus 3 times 6.67 squared minus 6 times 3.33 squared. Yes? No? Maybe? Okay. So that's 150 minus, we can make that 3 times 20 over 3 squared minus 6 times 10 over 3 squared, right? No? 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 Okay, don't believe me. And if we work that out, that's 150 minus, 400 over 3 minus 100 over 3. Yeah. Yeah. Is 150 minus 133, roughly. It's about 16. Okay, unless I screwed that up, and you're not here to tell me, so I don't care. So let's come back over here. Zy equals minus 12y minus lambda equals 0. But now z lambda equals 12 minus x minus lambda equals 0. So now x plus y have to add up to 12. Yes? 12. 12. Okay. 12. No. Fine. So we still get that x equals 2y, right, if we do the math. Yes? No? X equals 2y. And 12 minus x minus y equals 0. So 12 minus 2y minus y equals 0. Y equals 4. And so x equals 8. And that fits my constraint, right? Is good. It's goodness. Yeah, goodness. It is. It's really goodness. Okay. Okay, it's goodness. Just trust me. It's goodness. Now, 150 minus 3x squared minus 6y squared is 150 minus 3 times 64 minus 6 times 16, right, is 150 minus 180 and 12 minus 192 minus 96. Yes? No? Okay, fine. So that's 150 minus 288 is minus 138. Okay, which I'm taking as the answer. Whether I got that right or wrong, I don't care. Pretty sure that's right, 138. Now it was, when we did this before, we said, oh, it's about 16. Now it's about 138. Go back to where lambda is. Okay? Lambda is the value of easing the constraint. And what we mean by that is making this number, in this case, bigger. Okay, and most of the time that's what that means. It's making that number bigger. So every time that we make that number bigger, this says, hey, we should get about, the value of this function should change by about 40. And in fact, in total, it changed by a little over 100 for the two of them, which is about kind of what we would have expected. Okay? It's telling us how much this number changes as we change this, and you should do it lambdas for small increments. So it's not going to quite match, but it's for small increments. Now, go back. Okay? These are the first order conditions, right? And these are the second order conditions. So if we have a generic problem, generic,